Looks like we're live. Hello everyone and welcome to yet another Zosin session. How about that? So let's make a little bit of an announcement and officially start the stream maybe. So it's a little bit slow today for some reason. I mean my computer. So red circle live on Twitch. And what are we doing today on twitch.television? That's right, that's what TV stands for. So today we're doing pixel graphics in C. How about that? That's actually rather interesting. So it's a very abstract topic, right? But this is because if I put specifically what I'm doing today, nobody's gonna join the stream because everyone is going to be scared of what I'm about to do. Right, so, but if I put something like very abstract, but also catchy, like pixel graphics in C, who fucking programs in C in 2022? Holy shit! Everyone's gonna click on the stream and watch the stream and see, holy fuck, this is so cool, I'm gonna watch that. But what we're gonna be doing today we're gonna be actually rendering Voronoid Diagram. Voronoid Diagram. So you can clearly see if I put that in the title, nobody would fucking click on the stream, right? So that's why I have to go for, you know, pixel graphics and C. So that's all what we're going to be rendering today. But I mean, it's actually a very simple thing, right? So you can read about that in a Wikipedia page, right? So I'm gonna copy it in here, and also I'm gonna put it in the description, right? So here is the Voronoid diagram, and essentially the idea for this diagram is that for each pixel, right, for each pixel of the image, you color that pixel with the color associated with the closest sort of point. As you can see, you have a bunch of random points on a surface, right? And with each point, you have an associated color, right? So, and for each pixel, you just calculate what's the closest point. Okay, so this is the closest point, and it has this like greenish color associated with it. That's why we're going to be coloring this thing with that specific color, and you get a very cool pattern. That looks like cells, right? So it looks like cells. I already done it before, and you can actually generate it in like using very dumb, straightforward algorithm derived from the definition I just described. And this is what we're going to be doing today, just an exercise. And there's also a lot of cool, like different, like a 5-head algorithms that do the tessellation, like geometrically and stuff like that. They're super fast, it's just like n log n or something like that. But this is not what I wanted to do today. I've gotten a pretty cool idea on how to implement such algorithm that would be parallelizable. Right, so essentially my idea is the following. So what if we take the coordinate of these sort of like seeds, or I don't know how to call them. I think seed is a pretty good name. Maybe there is a like official name in the Wikipedia page. I didn't read the Wikipedia page, I don't read things. So we take the coordinates of this seed, and we pack these coordinates into a single pixel, right? So we have like, if we are doing RGBA, we have 32 bits, right? You have 32 bits, and you can split 32 bits in half, and you get 16 bits, 216 bits, right? And how much you can put into the 16 bits? You can actually put quite a lot. So this is going to be like your upper limit for the resolution. So this is actually quite huge resolution. We're going to be probably using something like Full HD or something like that, but we probably never gonna exceed this like amount of stuff. Right, so we literally pack it into a pixel, and essentially we do n iterations, right? So, and n is the amount of the seeds, and every time we just fill all of the pixels with the coordinate of the seed. Then on the next iteration, when we are about to iterate on the next seed, we fill with the new seed, but only when it is closer, if the pixel is closer to the original one, and we do that n times. So, and because of that, you can actually do that in parallel. You can split the entire screen into sections, and you can do that process in parallel, right? So, and furthermore, you can probably even port that process into GPU shader, Right. So essentially, you can probably write like a fragment shader that will do that on a texture, right? So you would probably have to do like and draw calls, and every time you generate a new texture with updated like pixel coordinates, right? And at the end, you'll get maybe the Voronoi diagram. I want you to try that. I'm not sure if we'll have enough time to like implement something sophisticated like GPU shaders or something like that, but we're gonna try to make a parallel version of this entire idea, and also maybe like using CMD for this idea as well would be also quite beneficial. We'll see. So today I wanted to just do like a recreational programming, like doodling around. I'm gonna implement like a very naive algorithm first to get the gist of what we're about to do, and then I'm gonna try to do the you know, my idea that I just described. So hello everyone, welcome. So how everyone is doing? Hello. So the trivial idea of going over all pixels and check the distance of all points is not parallelizable. It is parallelizable, but how easy it is to port that to a GPU shader, for instance? Like, you would have to somehow upload all of the seeds to GPU so they're available to fragment shader, and then in the fragment shader you'll have to do the loop or something like that. So I want you to design something that is portable to a fragment shader. We're probably not going to implement the fragment shader, but I want you to just try the idea. Right, so, and with the fragment shader, it's actually quite easy. You just like do n draw calls, and every time you sort of refine the texture, getting closer and closer to the diagram, adding more and more seeds. You know what I mean? So that's basically was the goal. So the original, of course, is parallelizable, but I'm not sure how easy it is to take the naive approach and just like port it to GPU shader or something like that. So this was just like a random idea. Does it make sense? Okay. Alrighty, so let's actually go and see. And to be fair, I have no idea how to port that to the shader. So I have a Voronoid diagram, and this is, oh yeah, this is the old project of mine which I implemented in OCaml, right? So yeah, I was trying to use like KD trees and stuff like that, but it's a very old project, right? So right, Voronoi diagram. We're not gonna be looking into that, but I already done something like that before. Oh, I even used like different norms, like to get different shapes and stuff like that. Look at that, that's so cool. So even like in -1, it's very interesting. Okay, I'm gonna actually put it in here. So, and then I'm going to put that in the description as well. Old Voronoi diagram project. So the reason why I was thinking about Voronoi diagram at all is because like a very long time ago, like 6 years ago, if you take a look, it's like 6 years ago, I actually did something related to that. So yeah. Alright, so let's actually go ahead and implement all of that. So Voronoi. Right, and let's create a simple C file. Simple C file. I don't know how successful I'm going to be with this entire idea. Maybe not successful at all. I actually didn't try that idea beforehand, so I just decided to try it for the first time on the stream, right? Because I wanted to stream something, right? Okay, so let's actually define, right, what's gonna be the size of the image, the resolution of the image, right? So we're gonna have width. Let's actually start small, like 800 by 600, right? Something like this. There we go. And we're gonna allocate some static memory, right, for the image, right? So this is gonna be uint32, right? So this is the RGBA, and then I'm going to allocate the corresponding arrays. So we're gonna store the image row-wise, right? So basically we just take the entire image and just straighten it up, and we have just basically rows stored sequentially in the memory, right? So this is basically what we have, and all of that is in the static memory, like so. I don't think I have to zero initialize this entire thing. I don't think so. All right. So, and then we need to have some stuff. Let's actually fill it up with something, right? Let's fill it up with something. We're gonna go y. Maybe I'm gonna actually do size t, y0, y less than. To be fair, I think I'm actually going too fast. I haven't even set up any build system for myself, right? So let's actually do something like this. I'm gonna comment out everything in here, right? And I'm gonna just say something like hello world, right? So we'll just say hello world and make sure that we can even build this entire thing. Right, let me see. Build sh and bin, why are you so slow? Okay, bin sh. Then I'm gonna set some parameters for the shell, basically the tracing, and fail on the first error, you know, the usual stuff. We're gonna enable some warnings, and Voronoi, I'm gonna like have this as the name of the executable, and we're gonna just build it like so. Alright, so another thing I want to do, I want to make this executable, and I'm going to run the build, and I'm going to start this entire thing. As you can see, we have hello world, we're good to go. We're good to go. This is the first success of the stream. We managed to print something on the screen. Isn't that exciting? Alrighty, so what do we have? Okay, let's actually go back and let's allocate some stuff. So for now, I'm going to fill the image with some certain color. Let's say we're gonna fill it with maybe red, right? So basically, I want to test things. So essentially, in this specific case, right, since we have LSB, least significant byte, right? So it's a little endian machine. That means to define some color, we have to use the following sort of template. So first comes the alpha, then B, blue, then G, green, and then R, right? And when you store that in memory, it's actually going to be stored R, G, B, A, right? So this is how it's going to be stored because it's a little endian machine, but when we write it as the hexadecimal literal, it has to be written like that, and it's just like something that I have to get used to. So, and this is supposed to be a red color, right? We can always do something like color red, and we can maybe save this entire thing in here, like so. So this is a color red. There we go, and let's quickly implement this procedure. You insert it to T color, right? Maybe for the sake of self-documentation, we can try to define a type def. You insert it to T, say color, or maybe even pixel 32. I think it's a pretty cool idea, right? So this is a pixel 32. Already color. Color 32. There we go. And in here, we're going to just iterate through all of these things, right? So this is going to be something like size y0, y is less than height, plus y, right? Then for size tx, width, plus x, right? And here we're going to do image y, x, color, there we go, we filled the image. So let's actually try to build this entire thing. It doesn't build because we probably need to include stdint. I'm also going to include stdlib just in case, right? Just in case, there we go. All right, so we fill the image, but we can't really see anything, right? So because we never actually save that image to, you know, to the file system, we can probably use stb libraries, right? But there is another cool trick. You can use ppm format, right? So I use that format all the time because it doesn't require any special libraries, right? Because it's a very simple format. So specifically a P6 variation of that format. So you can find the description of this thing in here. So let me find P6. I don't think there is like a P6. There's a P7 even or something like that. So let me find P6. There you go. P6, it basically has text metadata header, right? And then binary pixel representation. So, and let me actually give you the link. I wish Google didn't put that garbage in the URL. Every time I have to like copy paste it somewhere, I have to remove it. Okay, so you can find this thing in here, right? And I'm gonna put that in the description as well. Right, so this is the ppm image format. Right, there you go. So, all right, so let's introduce something like save image as ppm, right? And we're going to accept file path. Right, we're accepting the file path, and there we go. What's special about this formula? Which formula? I didn't put any formulas in the code yet. Are you guys okay? Okay, so let's actually open the file. Fopen file path. Right, and let's actually do write binary. And then we're gonna close this entire thing. So what we need to do, we need to put some sort of a header, right? So if I remember correctly, the header goes like this. You have to indicate that it's a P6 variation of the format. This is what I remember. I'm doing that off the top of my head. Right, then we have to provide the sizes, right? So this is going to be width and this is going to be height. And then you have to put 255, which stands for like the size of the component or something like that. So yeah. Oh, so what's special about this format? I'm sorry, like for some reason I can't read. There is nothing special about this format. That's the point. That's the point. So the problem with PNG is because it's too special. And with any other format, in fact, it's too special. It has its certain header, it has its certain way of compressing things, storing things. It has so much shit that you don't really need if you just want to generate an image. The point of ppm is that it's not special at all. It's just raw. You just dump bytes and there you go. You get an image. That's the point. It's an opposite of being special. You know what I mean? Right. So it's as unspecial as possible. And it's even older than me, right? So it's 34 years old. There you go. Or it's literally raw format. That's what it is. It's literally raw format. Okay. So what's going to be the next thing? We need to store the bytes of the image, right? So we need to store the bytes of the image. But as far as I know, in P6 you just store each pixel by 3 bytes, not by 4. So because of that, we'll have to sort of extract the components and just like put them in a byte array and then save that byte array to the file system. So that's what we'll have to do. So let's go ahead and do that. So this is going to be something like this: y0, y height, and let's do the following thing. Now, let me see. So we need to extract the components, right? We need to extract the components. Let me see. So maybe I'm going to do something like 8 bytes. How are we going to be storing all of that? So let me see. I need to extract a single pixel. So this is image, y, image. So maybe I'm going to actually store this thing in here. Right, so this is a pixel. We're talking about a single pixel. So first component have to go there. So just to remind ourselves, like, what are the components? It's AA, BB, GG, RR. Right. So that means to extract R, we have to take the pixel and just extract this, pixel. Right. Then we need to extract green. Right. I might as well actually align this thing so it's clear what exactly I'm extracting. But on top of this entire thing, I also have to shift it to the right. Right, and how much I have to shift it? I essentially have to shift it 8 bytes because it's a single byte. Right, so, and yeah, that's basically it. So I might as well maybe indicate something like this, so to align things accordingly. So, and then I have to take another one. Right, so this is gonna be something like this, so this is 16. Right, it's more of like 2 bytes. Right, this is a single byte, and this is the 0 byte. And there you go, so we extracted the bytes. It's pretty cool. Now I have to do fwrite. So this is going to be bytes, and then I want to just take the size of this entire thing. I don't quite remember. Right, I don't quite remember. How do you do that? So first is the size of a single element, right, and then the amount of elements. So here we get that, and then we put 1 in here. Okay. So, and yeah. So we probably also need to check for some errors. You know what I mean? Right. So we need to check if f is equal to null, we have to throw an error, right? fprintf std error. We're gonna say something like error could not write into file this because of that, right? File path, and then str error no, right? And then this is going to be exit. So in here, I don't know if I want to keep checking whether this operation succeeded or not. Alright, so maybe I'm gonna do the following thing. I'm gonna just assert that this thing didn't error out, right, and that's it. Because, I mean, if I successfully open the file for writing, so the probability of this thing failing is quite low, and I don't know if I want to do that. I'm gonna just assert just in case. So, and when I do fclose, I don't quite remember, right, so it can return, so we might as well even check this thing here as well, right? So it's going to be assert return has to be equal to 0, right? So do we return anything in here as well? Probably not. Okay, so that should be fine. So alrighty, let me see, and then we have to save image as ppm, right? So, and here what we're gonna have, we're going to just save all of that into, let's actually put that output file path, right? So this is what we're gonna have. It's an output file path, and we're gonna store it somewhere here. Output file path, output ppm, right? Output ppm, and let's try to build that and see how it goes. Okay, so we don't have a string. Let's include the string. So what else we don't have? We don't have error no. Let's include error no. Right. What else? We don't have assert. Let's include assert. Sure. Why not? Now, let me try to run the Voronoi, and we got a ppm file, and if I open it, it's completely fucking red. How about that? Isn't it cool? So in fact, I can actually fill it with literally any color, right? So we can maybe define more other colors, right? So this is going to be green, right? So this is a green color, and this one is going to be a blue color, right? So this is blue. So, and then I can try green, right? So I have to recompile everything before I can actually test that. Right. So, and as you can see, it's a very simple format. Like to save in anything in that format, right? To save anything in that format, I need only 24 lines of code, right? So it's literally 24 lines of code, no separate library. And of course, this format is not suitable for storing the images, right? You don't want to store images in that format because it doesn't compress anything or anything like that, right? But it's useful for generating images, right? So it's very useful for generating images. Okay. Anyway. So now we can also test the blue, right? So let's actually see the blue. So there we go, here's blue. That's pretty cool. So let me see. We managed to do that. So we need to do the next step, right? So we need to generate like a bunch of random random points, right? So, but to do that, we need to define maybe some sort of like a structure for the point, right? So let's actually define a point, and this is going to be x and y. Generate image in ppm format. Yeah. Did you go to school or just learned on your own? Why do you ask it like it's some sort of like mutually exclusive things? All right. So let's define some stuff in here, right? So how many seeds we're gonna have, like seeds count. So let's say we're gonna generate like maybe 10 of them, right? So we're gonna generate 10 seeds, and let's define something like point seeds count. Right, there we go, seeds count. Generate random seeds. Generate random seeds. So it should be pretty straightforward, right? So we just iterate through the seeds count, right? Less than seeds count plus I, and seeds I x is gonna be a random value from 0 to width, right? From 0 to width, and y is gonna be from 0 to height. Right, there you go. And that way you get, you know, random seeds. But it would be nice to maybe see them somehow, right? So maybe we can just render them, right? Maybe we can just render them. Let's implement a thing called fill circle, right? And in the fill circle, we're going to provide the coordinates, right? X and Y, right? X and Y, and maybe also the radius, right? So this is going to be radius, and also probably a color, right? So we're filling the circle with a certain color, unimplemented, right? So for now, it's not going to be implemented yet. So let's actually put something like maybe fill circle, right? So we already have a procedure that fills the entire image with some color, right? So we have something like that, and then we're gonna have another one which is basically fill circle. All right. So how are we gonna be filling this certain circle? So essentially, let me actually put it this way. Right, so we have some sort of area, and we decided that we're gonna render the circle somewhere here. Right, so we're gonna take the radius, we're gonna subtract radius from x and y, and we're gonna define this as the corner of the square, and then we're gonna take the center again and we're gonna add the radius, and that way we sort of defined the a certain rectangle within which we have the circle, right? Then we're gonna iterate pixel by pixel throughout this rectangle and just check if that pixel is inside of the circle or outside of the circle, right? So and then depending on that, we're gonna either put the color there or not put the color there, right? Pretty straightforward, right? And we're gonna have a way to put some sort of markers on the image to indicate some information, for instance, where the seed is located, right? So I think it's quite important. Okay, so let's define something like x0, which is going to be x minus radius. And then I'm going to call this cx and cy to say that it's sort of like a center, right? So we're going to do this is a center, and this is minus radius, right? And this one we replace minus with plus, and here we replace this stuff with 1. So that way I can now define x starting from x0 up until x1, like so. Then we're gonna do y, y0, y less than y1 plus y, Right, and in here we need to find the distance between the current point and the center. So we have to do something like dx. So this is going to be cx minus x, and the same goes for y, right? And then what we need to do, we need to find the distance, right? So to find the distance, you have to take the square of the, dx and plus square of dy, and then do square root. And then you have to check if it's less or equal than the radius. Right, but there is a very common trick to avoid square root. Right, if you don't square root, that means you have to compare it with the square of the radius. It's going to be literally the same, right? So you don't really care about specific distance. You don't care about the distance. You only care if one distance is bigger than another, but you don't care about the distances themselves, right? And because of that, you can just like do this kind of thing. And it's literally the same as if you did something like that, right? Something like that, but without the square root. Right, which is going to be faster, which is not going to depend on the math library, which is not going to involve floating points, and so on and so forth. You know what I mean? Right, so it's just like overall less complex, right? You can do all of that entirely in integers, right? If you're going to compute some stuff by using integers instead of floats, always go for integers, right? Always go for integers because you reduce the amount of mistakes you can make, right? Because floats are like very finicky, right? It's so easy to get them wrong or, stuff like that. So yeah, and if it's less than the radius, we have to just go ahead and essentially put this thing in there, right? But here's an interesting thing. All right, so x can be outside of the completely outside of the image, right? So we need to check for that as well. So how we're going to be doing all of that? If x is between this thing, only then we're going to go for this specific row. And within this entire thing, if y is within this entire thing, only then we're going to do that. Right, there we go. So that should be pretty straightforward, right? So that way we managed to render the circle, hopefully. We haven't tested that yet. We'll see, we'll see. Aiden Witz, I hope I pronounced your nickname correctly. Thank you so much for Twitch Prime. Thank you, thank you, thank you. And welcome to our epic Circle Club. So... Okay, let me see. So I'm gonna keep this comment in here because why not? So I want to actually fill the background. I think it would be nice to define something like a background color, right? So, and this is what we're gonna have. We're gonna fill the image with a background color. We'll have to define that background color. Define background color. Let's define something like my favorite background color is the background that I use in my editor, and the background I use in my editor is actually 808080 in hexadecimal. Right, so this is literally this background. Right, so we're gonna generate random seeds, and then I'm going to iterate through the seeds, and I'm gonna render markers with them to indicate where they're located. Right, so this is what we're gonna do. So we're gonna have seeds count plus I, right, so plus I, and then I'm gonna fill the circle seeds ix, seeds iy. What's gonna be the radius? Let's actually define something like a marker, maybe seed marker radius, and then we're gonna have seed marker color. Right, something like that. We're going to define two of these things. And if I try to compile this entire thing, as you can see, it's not going to compile because we need to define these constants somehow. So the radius is going to be, let's say, like 10 pixels. And the color, I think it's going to be straight up white. And let's define something like color white, which is basically all Fs. Right. So what do we have? It didn't like that because it's a color white. Right. So, and let's take a look at what we've got. We've got 10 points. Is it 10 actually? It is in fact 10, right? So this is basically 10 random points. We just generated them. I would say that the marker radius is too big, right? I think it's a little bit too big. I would go for 5 pixels. All right. So furthermore, I can do a pretty cool trick where I can just open this image, right? And I can like put outer revert mode. So that means every time the image is updated, it's going to refresh the image. And for instance, I can play with those things, right? So I can go to here and update this entire thing, and all of that is going to work. And all of that without any special software, right? So essentially what I'm using here is just the Emacs outer revert mode and a simple PPM format, right? I can put color red in here to make them red. So I didn't code any visualization of the image or anything like that. It's just like, yeah. So that's what's cool about these simple tools, right? So, but for now, I don't really need like something super big. I just like need a bunch of things in here. So, all right. So that's pretty cool. Isn't that cool? Isn't that cool? Oh, I think it's pretty fucking cool. 3 Windows development, yeah, exactly. So imagine being a Windows development when I'm 3 Windows development. Oh, by the way, the other day, I actually like was going through some pretty hardcore nostalgia because I tried to do Win32 API coding like on native Windows, right? And I had such a flashbacks to the times when I was in school. It's so cool, right? I almost forgot like how it was, like you know, creating the window using Win32 API, right? Like registering a class, right? Then creating a window, showing the window, organizing the event loop, all of that, like old school Win API stuff, right? So I did all of that while being natively on Windows. It was so cool, right? So, and I also did that with the Notepad++. And I compiled through the, you know, the development console of Visual Studio, right? Like old school stuff. Just like, holy shit, I remember. It brought me back to like 2009 probably. Yeah. Been doing this kind of shit in 2009. So, and of course, I forgot almost everything, but I just Googled this stuff. I remember how roughly do that. So I remember what to Google for to actually, you know, get the stuff, right? But I haven't done this kind of development for a really long time, right? But anyway, so maybe this is something I should try to do on the stream, but I need to set up like streaming on my Windows machine. I don't know, it's just too much. I don't want to do that. Too lazy, sorry. All right, so we generated random seeds. Maybe we need to render seed markers, right? So this is going to be a render seed markers, and I'm going to just tuck all of that code behind that function, right? Like so, render seed marker. So it's actually multiple of them, right? So it is actually multiple of them, so there you go. And it wants to update itself. Okay. Maybe I'm not going to do it like that, yeah. Okay. So the time has come to generate the Voronoi, right? So let's do something like render Voronoi based on seeds. Right, so there you go. So we're gonna fill the image with the background color, then we're gonna generate the seeds, and I'm going to render Voronoi based on seeds. Maybe, like, I mean, obviously it's based on seeds. I think it's like a waste of space, right? You render Voronoi, and we're gonna render the markers on top of the Voronoi, right? We're rendering them on top, because otherwise they're not gonna be visible. Okay, so, and we just need to implement like a direct definition of Voronoid diagram, right? So direct definition of this thing. So let's go ahead and do that. So it's going to be from 0 to height, right? Something like that. Then x width, plus x. And so after that, we need to iterate through each individual essentially seed, right? So let's actually define something like size t less than seeds count, right? Seeds count. And in here, we need to find the distance, right? So dx is going to be seeds ix minus x. The same goes for y. There we go. So, and what we need to do, we need to check if the distance to this thing is less than the distance to other thing. Which is quite interesting because we have to do the square distance, if you know what I mean, right? We have to do the square distance. Maybe it makes sense to actually take the square distance calculation and put it into separate function, right? So let's actually do something like this, right? SQR distance, right? And here we're gonna accept x1, y1, x2, y2, right? And in here we're gonna just like repeat the code that we're already trying to do the second time. x1, x2, same goes for y. And well, of course, here we have to return integer, and we return dx plus dy. There we go. So we basically compact that into a single function. So in situations like this, we can just do SQR distance cx, cy, xy, and just remove this entire thing. So we just compress this a little bit because we'll have to compute two of such things, right? We'll have to compute two of such things. So, okay, it also means that we need to remember the previous seed, the index of the previous seed. So maybe we're gonna actually store it in here, right? So this is gonna be the index of the previous seed, and -1 is gonna indicate that we found a seed at all, but maybe we should just like put a 0 in here. So we basically take the first seed and assume that it's the closest one. Right, it's the safest thing to assume. Right. So and what we need to do in here is just like take SQR distance from seeds I x, seeds I y, x y, and the second one is going to be the one but with j, right? Oh, and by the way, since we just took 0, the first seed as the one that is closest, we can start iterating from 1. Right, so it's just like something that we can do. All right, so what we can do in here is that if we found a seed that is closer, right, if we found a seed that is closer, we can essentially, I just realized that I don't have a shield behind my the camera, so I have no idea if you guys see everything that I type in here or not everything that I type in here. Right, so just like a simple indication that I would like to have, but unfortunately I don't. Alright, if we found something like that, I just like reassign j to I, right? So we found something that is closer. There we go, right. So, and after this process, right, after this process, we have to take this index and color the current pixel, right? Image yx related to this corresponding pixel, right? So we need to generate like a palette, if you know what I mean. We need to generate some sort of a palette, yeah. Let me try to find that. So what kind of palette should we use? We can try to use Groovebox. Groovebox palette. Groovebox palette. I can, when I type word palette, I can never remember if I have to put double T or double L. Right, for some reason. I don't speak English, I'm sorry. Okay, so give me that. So we're probably not gonna use like the background and foreground. We're probably gonna use these colors, right? So red. I wish there was like a thing that I can copy paste. Is there copy pastable colors, please? I want to have copy pastable colors. Okay, so we have colors. Groove box. Where are the copy pastable colors? Here they are. Here they are. So we have dark, light, bright red. So this is what we want, right? So suppose this is what we want to steal in here. You know what I mean? Right, so we're gonna be stealing that shit in here. And I'm gonna copy paste that stuff here. So let's do a little bit of a Emacs magic. Okay, so I'm gonna just take that. But that's not enough, right? Well, that's not particularly great, because what I need to do in here is probably just save these names, right? I think these names are important. Then I can define groove box, right? Groove box, bright red, blah blah blah, right? And in here we can put this stuff in here. So the problem here is that we have to reverse the components, right? So this is going to be FF, and we need to take, this is the red is in here, so that means it has to be put in here. The green is in here, so it has to be put in here. And after that, we just need to connect all of these things together. There we go. So, cool. And now we can define, you know, the palette, right? So we need to define the palette. So it's going to be color, but the color is defined. So where is the color defined? So let's define something like static color 32 palette, right? Palette. I don't know how many things are going to be in there, but it's just something, right? And I'm going to just like put those things in here. So a boom, a boom, a boom, a boom. There we go. Look at that. So I also want to have like a palette, you know, palette count, right? So we're gonna have static, maybe not static, maybe define palette count, right? So it's a size of palette divided by size of palette 0, just in case I'm gonna also wrap that in parentheses, because who knows. All right, and we have a palette, right? And how we're gonna be applying that? Again, we've got an index. Right, and we can just use that index as the index in the palette, but the index could be bigger than the amount of colors we have. So what we have to do, we have to probably wrap it around, right? So it's going to be palette, how we do that? Palette count. There you go. So it's going to wrap around. We're going to like basically go. We're going to rotate the colors every time. That makes sense. So we are rotating the colors. Okay, so we're generating some stuff, and look at that. This is mother flipping Voronoid diagram. Dap. Okay. So I probably want to actually render the markers with like a dark color, right? So let's actually define something like black, right? And in the black, we're gonna just put all of the zeros in here. So where's the markers? Have to be color black. Okay, so let me see. And yep. So that looks like a Voronoid diagram from the Wikipedia, actually, roughly, right? So it just like depends on what kind of like seeds you put in there, but they are like tend to go into like center in here. So that's pretty cool. We can actually initialize this thing. So let's do srand times 0, right? Srand times 0. And of course, we probably need to include time, right? So, and let me take a look. So, and every time we're gonna have like a different thing in here. I can even try to do that. So because I need to do auto revert. That was weird a little bit. But, okay, there we go. Yeah. That's pretty cool. Like every time I do that, it actually generates like a new fresh one, which is very cool. Let me now go ahead and find the seeds count, and let's say we're gonna have like 20 of them, because why not? So we're gonna have more of them. The more of them we have, the like more interesting this thing is gonna become, hopefully. But it's actually getting super slow because it can't refresh that properly. Right, but you get the idea, right? You get the idea. So now I want to try that idea where I essentially do that in n iterations, right? I already described that idea at the beginning of the stream, but for those who just joined, I wanted to try to generate that slightly differently, right? We're going to do a slightly different approach. So essentially, we're not going to fill with the colors, right? We're not going to fill with the colors. We're going to fill with the coordinates. We're going to literally take the seed, right? And we're going to pack it into the pixel, right? Into 32 bits. And then on the first iteration, we're going to take the first seed and fill the entire screen with that seed. Then we take the second seed and we start filling up with the second seed, but only when it is closer to the original point than the seed that is already stored with the pixel, and so on and so forth. We're going to do that iteratively until we basically like filled up all of the seeds. So that approach, as I already said, is potentially implementable on things like GPU, right? Because that will allow you to create like a fragment shader, right? A fragment shader that takes a texture. Within the texture, you have packed coordinates of the seeds, and with a simple logic, you can actually substitute, the current seed with the new one if it is closer to the current point that you are in, right? So I'm not saying that we're going to implement that today because I'm not sure if we're going to have enough time, but I want to like try this idea and see if it works, and if it works, it may potentially be implementable like on things like GPU. So, yeah, and like setting up the OpenGL and stuff like that, like figuring out how to pack that into a texture, it's kind of a pain in the ass. But maybe I'm gonna do that off screen, and if I succeed, I might do like a separate stream where I would show that, yeah, there you go, you can just like do that in a shader. That would be actually kind of cool. So maybe we're gonna split all of that into streams. But before I go into trying to implement all of that, I want to try to make a cup of tea. So let's make a small break. Right. So let's go ahead and try to implement that idea. To implement that idea, we actually need to pack the coordinates, the seed coordinates, into the caller, right? So maybe we're gonna literally just make a function, right? A seed to caller, right? And it's going to accept a seed, right? So point, right? Let's do it like this, point to caller, right? So this is a point, and we're going to return like a caller 32. So it's quite important that we do not exceed the limitation of uint 16t. So essentially what we need to do, we need to pack two integers into uint 32t. Right, so this is basically the result, right? We need to pack it. How can we pack it? We can split it into two uint 16s, right? So the lower one, let's assume the lower one is going to be x, right, and the upper one is going to be y, right? So we will have to somehow convert p into these corresponding things. I don't really know how yet. And then what we're going to do, we're going to take x, and we're going to OR them together, but for y, I'll have to shift it to the right 2 bytes, right? So I'll have to like shift it to the left. I'm sorry, I confuse the left and right all the time, right? So something like this. Maybe even like this. Since we're shifting to the left, I want to put y to the left, and this is how I pack those things together. And this is what I need to return, right? Maybe I'm going to merge these two lines together, right? So I'm going to just return this thing like that. So what we need to do now, right, is somehow put X and Y to here. We can literally do it like that, right? So, and it will kind of work. The compiler will actually convert everything accordingly. But what if px, for instance, is negative, right? So we probably want to catch that. We can just basically disallow these things to be negative, right? We can disallow them to be negative. All right. And another thing, what if they actually exceed the limit of 16 bits? We need to know what's the limit of 16 bits. Right, so it's 2 to the power of 16, it's 65,536, right? If it's greater than that or equal to that as well, so you won't be able to pack it there, right? So that means it's too big. We wanna be sort of notified by the program when we try to, you know, operate on such big resolutions, right? Of course, like this method is interesting, but it sort of applies a limitation on the resolution that we can use in here, right? So, but that's the price we probably want to pay or don't want to pay. It's just we have to pay it if we want to use this approach. So that's it. Like, it doesn't mean that we have to or don't have to. If you want to use this approach, that's the price you pay. If you don't want to pay this price, like, use a different approach. All right. So we've got 5 gifted subs by Scuba Craving. I hope I'm pronouncing it correctly. Thank you so much for gifted subs. Thank you. All right. So, but as far as I know, like, we don't really have to calculate that limitation. We can just get that limitation, right? So I think C has the thing like int limits, if I remember correctly. So, and we have everything there, right? It's just like literally limits. Why Google shows me this thing? Could you just show me like a more reliable source of stuff? Let's actually go to Microsoft. I trust Microsoft more than these search engine optimization parasites. Right. Okay, so let me see. There's only that, but there should be also integer types. So I probably need to go to CPP reference. Can I go to CPP reference? Yeah, numeric limits. Tutorial points. Yeah, exactly. Really? Like, I remember that there was like a way to know specific limits, right? Like int 16, but I can't see them here. This is so weird. Where are they? Where are they? Oh, I don't see. C++ documentation. Because if I have like a int 16 max, do I have something like that? Where is it located? In which it's std int, I suppose. Okay, so maybe I can just like do it like that. So, and what I want to do, I want to just assert that this thing is less than that, and y as well. Right, there you go. And let's try to build that. It seems to be building, right? So we don't have any mistake. So yeah, so just in case, I'm gonna also introduce an error just to see that everything's okay. Cool. Now we can go ahead and essentially fill a certain seed with like everything. So here we have a random like render Voronoi, right? So we render Voronoi. Let's mark it as naive. Render Voronoi. This one is naive. And let's introduce another one, which is basically render Voronoi interesting. I don't know how interesting it actually is, but this is something that I want you to try, right? So interesting. So how we're going to be doing all of that? We're going to take the first seed, right? So this is the first seed, which is 0. And I'm going to convert it to a caller, right? So this is going to be colors 32. Point to caller, right? And then we're going to fill the image, right? We're going to just start with the first thing. So essentially, the caller is probably going to be weird. Right, the caller is going to be weird because we're literally interpreting a point as the caller, right? So, and what I want to try to do, I want to try to literally save that. like literally try to save that and see how it's gonna go. Let's go ahead and do that. Right, so something didn't work because it's seeds, and there we go, so it kind of worked. So let's take a look at the output ppm. So as you can see, it filled it with the color. So this is the color of the first seed when compacted into a color. Like, you know what I mean, right? So we took the coordinates of the first seed, we packed it into color, and that's its color, right? So we're literally interpreting the coordinates as the colors, which is rather interesting. We can try to maybe also indicate that specific marker, right? But I wonder how difficult would it be. So we render the markers after we rendered the interesting diagram. So maybe because of that we want to move it somewhere here, right? So we render seed markets, and then I want to render another marker like fill circle seeds 0 seeds 0. So this is X and Y. And then we're gonna do the radius, right? So it's gonna be seed marker radius. So this is the radius, and the color is gonna be like, let's just use the color white, right, to sort of like indicate where it is located. And let me open this entire thing. So this is the color of this point, right? The color of this point is red. So, and what's funny is that since it's random, it's going to be different every time. The color is going to be different every time. The color of this thing is that. In fact, this gives me a cool idea. Do you guys know what kind of idea I want to test? Do you guys know the idea we're going to test? So each point on this thing has a certain color. What if we generate a gradient of them? Right, because, yeah, so each of them has its own color, so we can try to generate the gradient just to see how they're gonna look. It's actually a rather interesting idea. So let's go ahead and do that. So, like, I didn't think about that, right? So that's a very interesting way to generate the gradient. All right. So render, I don't know, packed, I don't know, point gradient. Okay. So let's iterate through the entire image. Right, so this is going to be like this, and this is height plus y for x, x less than width, plus x. This is my real voice, by the way. I have several real voices. What that's supposed to mean. Okay, so, but here I have to actually construct a point, right? So I have to do something like this, x and y, and then I can do point to color, all right, and then image. I feel like it's not going to be anything special. In fact, I think it's not particularly special because it's like x plus y, but y multiplied by a certain value, right? So it's not particularly that special, but maybe it's going to be something interesting. Anyway, so render point gradient. So I just want to see render point gradient. And there we go. So let's take a look. It makes sense, actually. So guess what's the size of this square? Guess what's the size? $256, yes, exactly. I'm pretty sure it is 256. It cannot be 6500 because it's too huge. It just cannot be 256 because it's a single component. Right, and we can even try to test that. Let me actually do it like with if 0 else, and this is going to be end if 256. Ooh, there we go. So if I open it now, yeah. So as you can see, it's literally that. All right, that's cool. So, and like everything is gonna look like that, right? So, It's kind of interesting, but yeah, it does make sense. It does make sense. Yeah, I really like to explore these kind of things, right? So just get an idea, just test that idea. So for me, this is what makes the programming enjoyable, right? So this is what I call recreational programming. Just play with things, explore things. It's all about exploration. Okay, so I'm gonna keep this thing in here and let's actually render Voronoi interesting. Right, so, okay, we put the first thing in here. So we filled the entire image with the first seed. So now we need to take the second seed, right, seeds 1, and actually combine with the current image. Right, so we need some sort of a function that takes the next seed and sort of applies that next seed to the current image that we have. We might as well even like convert it to color right away. But I need to come up with a name for this function, right? And this function is supposed to do the comparison. So I'm gonna start implementing this thing, right? So this is gonna be color 32 and this is the color. And essentially what we're doing, we're iterating through the entire image, right? So literally through the entire image, we are iterating. So it's going to be y less than height, plus y, x, 0x width, plus x. All right. And what do we have? So essentially, we have 2 points. We have a point encoded in image yx. So we have a point stored in here. This is the first point. The second point we have stored in here, right? And basically, depending on which point is closer to xy, we have to save it there. You know what I mean? Right. So depending on this kind of stuff. So I suppose first thing we want to do, we probably want to decode that point. Right. So we need to decode that point somehow. Let's do color to points. So it's going to be an opposite function. So we already have points to color. We have to do an opposite thing. Right. Point color to point. And here we're going to accept color 32. This is C, and we just have to do this thing, but opposite. Point P. So X is essentially C and FF. Right, so the low 2 bits. Another one is C, FF, 0000. We might as well even put it like that to align to see exactly what kind of bytes we're extracting. And after that we want to shift this thing to the right, like by 16 bytes. So effectively here we're shifting by 0 bytes, right? And here by 16 bytes. This is how we extract that, and we want to return this entire thing. I might as well actually merge these 2 statements together by doing something like this. And there we go. We just unpacked the point, right? We just unpacked the point. Maybe it's too much. Maybe it would have make sense if we created some sort of a struct point 32 uint16t uint16ty. Maybe that would have been better. Which is a rather interesting idea actually, but is the size of point 32 is going to be exactly 4 bytes? That's the good question. Or is it going to be like padded somehow with it, you know, to maybe 64 or something? Probably not. I don't think it's going to be padded, but we can always test that. Right. So I'm going to just put it like that, and I want to print something like size of point 32, and it should be equal to size of point 32, and let's see its size. So we can't really do that because we didn't put a semicolon in here. So parameter without declaration something. Oh yeah, so this one is the, so this more of like a new point. Okay, so I'm gonna just, you know, comment it out for now because I want the code to just compile because I want to see the size. Okay, it's exactly 4. Right. So, which brings the question, like, do we really need to, like, worry too much about this kind of conversion all the time? Because what we could do instead, I think, we could take our image. Where is the definition of the image? So here's the image. We can do something like 0.32, right, 0.32. Let's actually take this entire thing and go back. So this is 1 point, this is a 0.32. So the difference between them is that integer, I use integer here as like any integer. I don't really care about the size, I don't really care about the sign, I just say that the coordinate is an integer. That's why I don't have any prefix in here, so the size, the signs don't matter, just like store somehow. I don't care. So in case of this, I do care. Not only do I care like how much it takes up this the size, I also care how it's padded, how it's aligned and stuff like that. And that's why I use like very specific things. So as far as I know, this is the approach of JAI, right? In JAI there are like types like S64, S32, 16, like there's all these different integers, but there is also always int. And int is specifically for that. Like if there are situations when specific int doesn't matter, there's just like some integer, right? And I use integer here like with the same sort of idea. Okay, so here we have points, and what I want to do, I want to create a pointer to this thing and say something like image as points, right? And I'm gonna assign an image in here. So I'm basically like reinterpreting the entire image as points. Isn't that cool? Well, I mean, it's probably... So I can probably do something like this. It's like a pointer to like these things, like rows. Yeah. There we go. Something like that. It's very interesting actually. So, and that way I can always like, if I have coordinates x and y, a certain coordinates, I can always just do image as point, right? And then access the components as like x and y. Right, something like this. Know what I mean? Know what I mean? Is it the same as casting? It is literally casting. It is literally casting. Or depends on what you mean. We're casting pointers, we're not casting the values behind the pointers. So casting a pointer and casting value behind the pointer is actually two different things. But I'm not sure how useful could it be, right? So I'm really not sure. Because what I can do, right? Oh, this is actually very cool. Right. Maybe not. Okay, so I'm not sure if I'll find any use for this sort of approach. Right, so I just want to implement something that is working, and then we'll see if it makes sense to do it like this or not. So... But with this kind of thing, I could have done like 0.32, right, and call it next seed, right, so this is basically next seed, and that way I don't have to unpack anything, right, I don't have to unpack anything, and because of that, like, how can I convert that, right, so I have a seed, I convert it as a color, but then I want to reinterpret it as a 0.32, but it's not gonna work, okay, we'll see. Right, so this is as points, and now what I need to do, so this is 16, this is 16, all right. But it all also heavily depends on, like, because if I want to compute the distances, right, I'll have to subtract signed things, So that's why I have to do that in unsigned, right? All of that stuff has to be done in unsigned. So that's basically the problem in here. So because of that, I probably want to do that with something like this. Color 32. Okay. Next seed color, right? And this is going to be next seed. Color to point. Color to point. Next seed color. Next seed color. There we go. So this is the next seed. So this is the next seed, and here we can have the current seed, right? So current seed, color to point, color to point. So and in here we have to compute the distances between them, right? So SQRT. So literally the same thing, but here we'll have to do if sort of next seed less than the current seed, right? Car seed. We have to reassign the next seed color image yx next seed color like so. So that's what we're doing in here. That's what we're doing here. And the question is, how do you call this function, right? I don't know, like apply next seed color. Like I cannot come up with a better name for this thing, so that's why I'm going to call it like that, next seed color. So as you can see, we add the color of the first seed, and then we're going to add the color of the second seed. And it sort of acts like a stencil, right? So you know that in OpenGL there is like a notion of a stencil. Right, and this kind of acts like that, if you know what I mean. Alright, so that's why I was thinking about like GPU, OpenGL, and like thinking how you can like put that on GPU. So anyway, okay, let me see. So this is the image. Yeah, so you have to explicitly cast that. So because of that, probably it's not a particularly great idea. Alright, so let's get rid of the alternative entry point and see if we manage to generate something. Okay, look at that. So essentially we generated two colors, right? It worked, but only for two seeds. Now we have to do that for each individual seed. We can even like try to print all of these things, right? We render the markers, and let me try fill circle seeds 0x seeds 0y. So it's going to be seed marker radius, and the color is going to be white. Right, then after we applied all of that, I would say we want to put it in here. Right, it's going to be 0, and this is going to be 1. Right, now, if I open this entire thing, look at that. So these are the colors of these 2 points. So this is the first one, and this is the second one. Right, so as you can see, we can sort of apply them independently. We can now add the third one, right? We can now try to add the third one. So this is going to be this one, and in here is going to be something like this. Right, and if I open it like that, so this is the third one. As you can see, I have the points of this third one, right? So you see what I'm doing in here, right? I'm sort of like recomputing the pixels for each seed individually. Like I can add seeds regardless of their order. I can add them in any order. And you know, the cool bonus is that I don't have to think about the color palette. The coordinates of the point is the color. Right. You see what I mean? This is actually a very cool approach. So, and we can keep adding those seeds, right? So we can add the fourth one. Right, so could replace 2, 3. And let's take a look. There we go. So this is the third one. Whoa, are you really from Siberia? Your pronunciation is so clean. How did you achieve this? I worked really hard on my pronunciation. Thank you so much. Really appreciate that. I worked in the outsource for quite some time. So, is there a gradient between the points or across the whole image? I don't think so. There should be no gradient, but yeah. Okay, so let's actually do the obvious thing. Let's do the obvious thing. Let's iterate through all of them, right? So 0. Actually, we have to start with 1 because we already applied the 0th one. Seeds count plus I, and we're gonna apply this thing like so, and should be fine. So this is sort of like a, it's sort of like an inside out, right? Because if you take a look at the naive approach, right, we're iterating each individual pixel, and for each pixel, we're iterating each seed, right? So we're iterating each seed for each pixel. But in here, we actually put it inside out, right? For each seed, we iterate in each pixel. So it's the same complexity, actually. It's the same complexity, but we put it inside out, which is rather interesting, actually, right? So, and what it enables us to do is like maybe coming up with some sort of a shader, right? That can do all that, because as I already said, you can put, I'm pretty sure you can put, where is that logic? Here it is. You can put this entire logic into a fragment shader, right? And the logic is going to be actually this, right? So because the fragment shader does this for loop for you automatically, right? So the fragment shader sort of like takes the fragments and applies a single shader to all of them, right? So, and in a single shader, we're going to literally have that. And it's relatively straightforward to turn this into branchless, right? So you can quite easily make it branchless. I can probably even do it right now, right? So this is the condition, and I can just turn this into something like this. So this is an integer, and if this condition is true, right? If it's true, I just multiply by the next color, and then I do like the opposite condition and multiply it by the current color that you have in here. That way, this entire thing became branchless. You know what I mean? Right, and you can do the same thing in the shader, right? So there's no branching in here whatsoever. I'm pretty sure that even the compiler, if you put if in here, right, it will still not generate a branch, because it's, you can use cmove like LE or a cmove L, right? So there's a conditional move that doesn't generate a branch. Aren't you doing what GCC should do? Well, yeah, effectively, but GCC should do something even more better, right? It's supposed to use the move instruction that is conditional. I can even show you something. All right, so let's actually go to Godbolt. How people distinguish Godot and Godbolt? It's the same shit for me. So let me do simp_c. Right. Let's imagine that you have a function x and y. All right. And essentially, if x is greater than y, we're gonna assign y to x and return x. Right. Essentially, this is the minimum. So this is implementation of minimum. So we always return x, but if x is greater than y, it becomes y. So if I put that in here, it should not generate any branch. As you can see, it didn't generate any branch, it just used conditional move. So it does something even cooler, right? So it just compares two arguments, and depending on whether it's true or not, whether the bit, corresponding bit of CPU was set, it will either do this instruction or not. So it's actually a very cool instruction in here. So cmove. So this is what I was hoping for, and I'm pretty sure GCC is supposed to do that for me, right? But I don't know if the like something like shader compilers do that as well. They probably do. All right. So Okay, we need to now test that, and that thing should just work. Huh. Oh, you didn't distract me. I think it's actually really interesting because, I mean, it's a part of the content as well. Maybe somebody didn't know that GCC does that, so it's a part of the content. Don't worry about that. I wonder what's going to happen if you put 03 in here. I'm pretty sure you can't optimize it. Yeah, you can't optimize it any further. It's just as optimal as you can get it. Strangely enough, why didn't move it to EAX right away? Like, why? Yeah, why do you have to do that? Is that because CMoveG doesn't work with EAX or something like that? Maybe. I don't really know. Maybe there's something like that, but yeah, there you go. So it worked. But I wonder which one is faster. Can you say definitely if something is more like fast than another one? So if we make a bigger resolution, right? So if we have a slightly bigger resolution, right? So that's the resolution we have. It's a pretty big resolution, and we can try to just like measure the time, Voronoi, and see. So it's around 1 second all the time, right? So it's around 1 second all the time. So, and if we switch to something else, right? So Voronoi native, render Voronoi native. Because here what we have to do, we have to also render the markers. Okay, I can just move them here. And let me build the entire thing, and let's just do time. And it's actually faster. So the approach that I chose is actually slower, right? So yeah, there we go. So this is the old generation, right? So this is the old generation, and yeah, it's always like around 800 milliseconds. But the approach, the other approach that I used, that I think is interesting, is actually slower, right? And probably because of the constant conversion and stuff like that, right? So probably because of different conversions and thing. But yeah. Kick W, yeah, kick W indeed. So really, the next thing I really want to try to do, I want to just come up with a shader that does all of that, right? So, and how would we implement that in the form of a shader? I suppose we would render into the frame buffer, right? We would render into a frame buffer and then take the frame buffer and turn it into texture and feed back into the same shader, but with a different seed to generate the next texture, and then the next texture, and then the next texture, and then the next texture, right? So, and yeah, we'll do that n times, but since like each addition, right, each apply happens on the GPU, it should be relatively fast, I think. So this is something that I would like to try. But unfortunately, I don't really have enough time to do that because I need to set up OpenGL, then like think if I can actually pack this like a point information into a texture or something like that. So that will be interesting to do, but probably next time. So, all right. What I'm thinking actually is that how can I avoid all of this conversion and stuff? How can I avoid all of this conversion? Probably can't avoid that, so this is something that I have to deal with. All right, so does anyone have any on-topic questions? So with moving seeds, it would be kind of cool if you could implement it as moving seeds. I think it's quite kind of interesting. But I think for moving seeds, you probably want to use like these 5-head geometric algorithms that actually like generate a mesh out of these things, and they're usually super fast, right? So very smart people develop this kind of algorithms. And what we do here, we're actually generating the image pixel by pixel, right? So which is kind of like, but this is something that I wanted to try. So yes. So the thing that I'm a little bit worried about actually is that if I have a texture, I have RGB pixels, right? RGB 32 pixels, whatever. So it's just like very specific pixels. But when I put it into a shader, I get them as vector 4 elements, which effectively kind of loses some information about the position, but probably not too much. I don't think it loses information too much, right? Because essentially what it does, it converts the components from 0 to 155 to 0 to 1, and you can quite easily convert all of that back to the specific coordinates that you want. So it should be relatively stiff. It should be doable, actually. It should be doable, but setting up this environment where you constantly like render into frame buffer, it's too much work. It's more than we have enough time for the entire stream. Can you use union to treat point as core 32? Yes, I can. So yeah, I think like putting all of that into shader should be really doable. Yeah, I'll think about that, and probably if I'm gonna do an next stream, and this is precisely what I'm gonna do. This is precisely what I'm gonna do. All right, so I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you next time. So today's stream was rather interesting. I just gathered a bunch of information, right? So some of the things that are obvious now were not obvious until I implemented it. So I think today's stream was rather interesting. So I think it was. All right. Thank you so much for watching. Love you all. Stay safe.